Okay, so maybe it's time to get started. You guys are the real enthusiasts for generative models. Thanks for coming. Thanks for waiting for the first 15 minutes. My name is Romit Roy Chaudhary. I'm a professor at the University of Illinois at Urbana.
My name is Yulin Wei. I just joined UIUC this year. I'm a teaching assistant professor at UIUC. 1 year before I was Romit's student, but now I'm super honored to be on the same stage with him.
Okay, so with that, we'll get started. Online audience, you can hear me from here, correct?
Yes.
Yes.
Good. So thanks again, and we can get started. So a couple of caveats before we start. We are pretty new to machine learning as well. So when we explain things, several things may not be clear. So anytime you don't understand something, it's because we are not explaining it well enough. So please ask questions. It's absolutely fine. And there's no silly questions, only silly answers. And sometimes we may not have answers, but someone in the room might have, so please chime in. We don't want this to be a one-sided 7-hour tutorial, obviously. Second, the audience, I expect the audience to be diverse. So it's difficult to find the correct balance between pictures, intuitions, and equations. So please slow us down, speed us up. If you find the math is too boring, know all of this, speed us up. If you think that, oh, it's going too fast, please slow us down. Totally fine. Especially with a small group, we have the ability to adjust. Okay, good. So here is the roadmap. We'll start the tutorial by doing a pass over the whole thing, right? So whatever we're going to talk about the whole day, we'll do this whole thing in a nutshell. And importantly, the nutshell will only be pictures and intuitions. Okay? Then we'll do a quick probability warm-up because we'll need a whole bunch of things throughout the day. So we'll do some warm-up, push-ups, not push-ups, jumping jacks, probability jumping jacks. Then we'll get into latent variable models, autoencoder, variational autoencoders, then hierarchical VAEs. So somewhere here will be lunch, halfway into hierarchical VAE, hopefully. Then we'll do diffusion. We'll do a little bit more diffusion and finish off with GAN and normalizing flows. That's basically the end session. And my hope is you will have a reasonably good overview of generative models, state of the art. Good. So let's get started. So this is the last slide of today. This is what we'll end with. And if you have little background in generative knowledge, then this is the big picture. Okay? So generative model is a neural network, is a black box to which we will show a lot of real pictures. And I'm showing you real pictures of faces, but it can be birds, dogs, cats, cities, trees. We'll show the generative model lots of real pictures. And then we'll say, generative model, train yourself. The generative model will get trained. And then at the end, we'll take that blue box and I'll give it to you. You take the blue box and you say, generative model, generate a picture of an old man, and it'll generate a picture. So generative model, generate a picture of a car, it'll generate a picture of a car. Right? That's the end goal of all the things that we've talked about. So model that you'll ask for certain things, or even if you don't say anything, you say generative model, give me a picture, it'll generate some random picture, and the picture should look pretty realistic. This is the goal. So in some sense, the model is looking at real pictures, learning whatever there is to be learned, and then on itself, it's generating new pictures and maybe generating pictures based on prompts that you're giving. Right? This is pretty baby stuff. All of you know this, but just good to start off with that. Now let's formulate the problem with pictures and intuitions. Okay? So any image can be thought of as a point in a very high dimensional space. Is that clear to everybody? Right? So for example, an image which is 64 pixels by 64 pixels, right? You can think of 64 times 64 as around 4,000. So every image is a point in 4,000 dimensional space. It's clear, right? So if I ask you, what are these dimensions? What are these axes? What are you going to say? 4,000 axes, right? 4,000 dimensional space means 4,000 axes. What does that axis mean? Let's say I take the first axis. What does that mean? What are these 4,000 dimensions? So a pixel is an axis, right? So 4,000 pixels, 64 times 64 pixels, right? Is 4,000 pixels. Every pixel is an axis. So you take the first pixel of the picture and you say, oh, this is purple. So on the first axis, which starts from black all the way to white, you say, where is purple? You say that purple value is for that first pixel. Now you do that for the second pixel, which is the second axis. You do that for the third pixel, which is the third axis, because every pixel has a color. So you do that for 4,000 pixels, that is some point in 4,000 dimensional space. Right? So any picture you can think of, if it's 64 by 64, it's a point in that 4,000 dimensional space. Good. Now this 4,000 dimensional space is obviously huge. We can't even imagine that. Right? Einstein was Einstein because people say he could imagine 4-dimensional space. Right? We can't do that. Right? So 4,000 dimensional space, if you think about it, I want you to think of it for a while, for a second. You're in 4,000 dimensions. You can go in many, many dimensions. You can walk in many, many dimensions. In 3D, if I immerse you in a desert, this desert is probably not even 3D. It's desert is 2D, right? 3D is I put you inside the Pacific Ocean, and I ask you search for your phone. It's dropped somewhere in the ocean, right? There's so many directions you can go to. It's very hard. 64 dimensions is much, 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 much harder. Right? So we'll visualize this 64 dimension like as if you're in a desert. And in this desert, every grain of sand is a picture. Does that make sense, right? We can't do 64 dimensions, it's 4,000 dimensions. So therefore we will do just 2 dimensions, but think of every picture as a sand. And if you take a random sand and you look at it, what do you think it will be? They'll all be noise junk pictures. Why? Because if you take a 64 by 64 matrix and you randomly put different values, it'll be a junk noise picture, right? Only few pictures will be realistic, will make sense to us. Okay? So in this 4,000 dimensional space, most of these points or sand particles will be noise. You'll find one that is a cat. You'll say, wow, I found a picture, great, right? And then if you look at the next sand particle, that might be a little bit noisy cat. Do you see that? Because this is also a picture. This is also a point in 4,000 dimensional space, right? It's just that these pixels have been noisy. This one happened to be the nice cat. Now, can you tell me if you keep walking along this line in that 4,000 dimensional space, along that line, what are you going to see next? You go in this direction, it's a noisy cat. If you keep going down, come on, no silly answers. Noisier cat, right? It'll get noisier and noisier, and eventually you'll get all noise. Right? So in the 64 dimensional space, there's one thread, you found a cat, and then if you go in certain direction, it'll become noisier, 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 and it'll become noise. Right? Very good. Let's look at some other pictures. Maybe this picture is a real picture of this lady. And this picture you look is kind of similar to this lady, right? Two pictures are kind of similar, right? So maybe there's a path that if you change pixels on this picture a little bit, you might arrive at this picture, right? So if you walk this path, you might come from this picture to this picture, so that picture will morph into the bottom picture. Does that make sense? Right? And maybe there is another path from here to here, even though this is a different lady. There might still be a path, which means every point in this path, you change one pixel, and then the next point you change another pixel, and then the other pixel, when you go to that. So you see that 64 dimensional space has pictures scattered around, and maybe there are connections between pictures. And if you walk only along that line, you will see correct, realistic pictures. But if you step out of that line, you might quickly start seeing junk. Right? This is called an image manifold. And this image manifold, as you can see, is very, very sparse. Which means if you randomly take pictures in that 4,000 dimensional space, it will be junk. Only when you're on that manifold, you will see pictures that look realistic. And now, it's not true that if you just step out of this manifold, you're walking on this white path, you just take a step in this direction, and you take a picture, it'll be some noisy version, but it could also be something like this. Look at this picture. This looks realistic, except that the eyes have come down. Right? So this is also a picture which lives in 4,000 dimensional space. Right? This is not noise, but it's unrealistic. So it's inconsistent with the rules of nature, with the laws of physics. Right? Similarly, here is a year that's not realistic, but you know it's a year. Right? So these yellow points will also lie in that 4,000 dimension. And if you step out of the manifold, you'll get these unrealistic pictures, maybe hands with 10 fingers, 8 fingers. And if you've seen generative models hallucinate, these are the kind of pictures it gets because it has stepped out of the true manifold on which real images lie. Questions? Good. And this is huge, 4,000 dimensional space. I repeat that because it's good to always have that in mind. So the image manifold, oh, it gets cut off there. Okay, so the image manifold is very, very sparse. And for the rest of the tutorial, we will think of the image manifold as this 2D orange space. And these green points will signify real images, realistic images. And the red points will signify noise or unrealistic images. Now, the goal of generative models is the following. Okay. Generative model says, these images that are realistic, who knows? How do you know they're realistic? The hypothesis is God has a distribution on this 4,000 dimensional space that God knows. And God picks samples from that distribution, and all the samples from the distribution are realistic images. Does that make sense? God has some distribution in mind. Maybe this is the distribution. And God picks samples from that distribution. If that distribution has high probability, then you'll pick a sample from that distribution, and that sample would be realistic. So God knows some distribution, and our goal, or generative model's goal, is to learn that distribution. Does that make sense? So there's some distribution from which samples are the realistic images that we see in the internet, or whatever realistic image. If I take a picture now of all of you from my camera, that picture is a point in 4,000 dimensional space. That picture will have a high probability in this distribution. Okay. Our goal is to take samples of real pictures from the internet, and then for those samples, fit a distribution that matches God's distribution. If I do that correctly, then what have I got? Once I fit that distribution that matches God's distribution, then from that distribution, we'll keep sampling pictures. We have solved the generative model problem. Remember that blue box, right? I want to get realistic pictures. So all I do is sample from that distribution. Is that clear? So the question, so this is the thing. The generative model's goal is to figure out this distribution. That's all. If I know that distribution, I've solved all problems. Right. Now the question is, how do you fit a distribution? If I give you a bunch of points, how do you fit a distribution to it? Hey, you can see that there are infinite number of functions that you can fit to those points, right? I give you a bunch of points. I give you a bunch of poles on this floor, and I say fit a distribution. So I can fit many distributions. I can do something that looks like this. This is fitting a distribution. I can do something that looks like that. That is fitting a distribution. Whatever you ask me, I fit I fit a function. So there are infinite number of functions that fit those set of points. How do you know what is the right? So one idea is what is called maximum likelihood estimate. So this basically says, look, I'm going to pick some function, let's say f of x, and I'm going to say if this function was true, then what are the probability of all the points, all the real data points, and I'm going to keep changing that function until the probability of all those data points get maximized. Does that make sense? Right? Imagine I have data points like this, just one-dimensional space. I pick a function which is like that, right? And if I take this function and I move this function over here, then for that function I can compute what the probabilities are for all those points. And I'll keep moving the function until the sum of the probabilities get maximized. And that is my maximum likelihood estimate. Okay? So one idea is I'm going to try to find that function which maximizes the probability of all realistic images. And this function I'm going to learn using a neural network. So the neural network is going to take an image as an input and is going to give me one output, which is the probability of that point. And if I have learned that neural network, then I can take input as any point in this space and I'll get the probability value. That gives me the function. So this is one idea that lots of generative models would take. But of course, it's not easy. That brings up many questions. One, how do you choose theta without over or underfitting? Guys, what is theta? When we say a function f theta x, let's be clear about this. What does theta mean? Theta are basically the parameters of the function. So let's say ax square plus bx plus c. Right? This is a second order polynomial. If I give you ABC, do you know the polynomial? You know the polynomial, right? So then theta is going to be ABC. Correct? If I give you, well, it doesn't matter. For the neural network, all the parameters over here is theta. Okay? And the neural network, remember, the neural network is a universal function fitter. Neural network fits very good functions by learning those parameters theta. So remember, if you want any kind of function, you first need to say you first need to design the neural network. And the neural network, if you have enough parameters over here, if you have enough layers, enough depth, then that neural network means that neural network has a lot of capacity to bend. If you have less number of parameters in the neural network it's stiff. It doesn't bend too much. Right? So you have to first choose a neural network in which you say, how much do I want that function to bend? And that's a design choice you have to make, which is why designing neural networks is hard, because first you have to say, whatever that God's function is, I don't know whether it's a stiff function, whether it's a flexible function, I don't know what it is, but I have to still choose a neural network, which means I have to still choose some flexibility of my function that is enough to capture God's function. Okay? So I choose the theta, and that's still kind of an art, how you design the architecture of a neural network. Okay, fine. Let's say I choose theta correctly. But now you have to ensure that f theta x is a normalized probability density function. Because remember, you wanted a PDF, you wanted a probability distribution. So the output of the neural network, which is a function, need not be a PDF, need not be a probability density function. Why? When is a function a probability density function? When you Normalized. When the area or the volume under the function equals 1, that's when it's a probability density function, right? So the neural network gives you a function, it's not a PDF. So now you have to figure out how to make that a PDF. Because at the end of the day, God has a PDF that God knows. Even if you figure out how to do a PDF, this function can be all kinds of a complicated shape. But if you want to sample from that function, then the question is, if I give you some function, can you sample from it? If I give you a Gaussian, you can sample from it. If I give you a uniform distribution, you can sample from it. If I give you an arbitrary function, can you sample from it? It's very hard. This is where things like Markov chain Monte Carlo, Langevin, accept reject sampling, these kind of techniques exist in advanced probability, where given a random arbitrary function, under certain assumptions, you can sample from that function. But those are very computationally heavy. Okay? So it's not even easy to sample from that function. Finally, suppose you figure out a way to sample from that function. Right? You got the probability distribution function that God knows. You got that function and you know how to sample from that function. And sampling from that function means, from this function, if I draw 100 samples, okay, then the samples that come from this region will be proportionally many more than samples that come from this region. So the samples, the part of the space where they come from will be similar to their probability ratios. Does that make sense? So high probability, you're going to get more samples. Low probability, you're going to get rare samples. Right? So here's an interesting question that's open. Okay. Suppose you figure out God's distribution and you sample from this function. Now, suppose, okay, let me back up one more time. You haven't figured out God's distribution. You figured out your own distribution, which you think mimics God's. That's what you're ultimately. Now, if you sample from your own distribution, you're going to get most of the samples from these high probability points, correct? Now, these high probability points are high because you've already seen data at those points, correct? So then when you get samples, the samples look very similar to the data that you've already seen. Right? Someone can say, what is creativity about that? What is generativeness about that? Generativeness should be, you should be able to generate an image that your training data did not see. But if you fit a distribution, you're going to sample from the distribution, then you may only get samples that are in this region. And this is the region where you've seen data, and that's why you've given it a high probability. In other words, generative models today are not creative. If you've shown it a face, if you've shown it my face, and then you ask it generate faces, it'll show you this face, maybe that face, maybe change my clothing a little bit, but it will not generate Yulin's face. That's not creative. That's kind of whatever you've seen, you make incremental changes to it initially. Creativity says, oh, even though you have seen data from here and here, you should still have high probability in some other region from where you have not seen data. That's creativity. Agree? I have shown you pictures of him and me, and the generative model can generate pictures of him. That's creativity, right? But to do that, to generate pictures of Suman, the mode, this probability for Suman should be high, even though the generative model has only seen pictures for Romit and Yulin. Agree? But then a lot of people in generative models and AI come and say, no, that's not the right thing to do. That's hallucination. Why is that hallucination? Oh, because how do you know a person like Suman exists? Right? And then, generative models once generated a blue butterfly. It saw orange butterfly, yellow butterfly, and it generated a blue butterfly. And is there a good news or a bad news? A lot of people says, wow, beautiful. It has seen red butterfly, it has seen orange butterfly, and it generated a blue butterfly, creativity. Some people say, you know what? Blue butterflies don't exist in nature. Why? Oh, there's some beautiful chemical theory which says that any natural organic material cannot be blue by themselves. So blue butterflies are inconsistent with nature. Generative models don't know that, right? They generated blue butterfly. A lot of people say this is beautiful creativity. Other people say that's inconsistent with reality because blue butterfly doesn't exist. So we have to be very careful when we say generative models are actually creative. They're doing all kinds of things. They're still not. First of all, because they've not figured out the line between hallucination and creativity. And second, they have no reason to put a high probability value on blue butterfly because they've not seen an example of a blue butterfly. Right? They only put high probability for training data that they have seen. And of course, if you've seen my face, it can, by sampling, if this picture is my face, if you sample around, you can get my face like this, like that, like this, and so on. But still, that is challenging. Because remember, around this point, you cannot say this is Romit's face. You cannot say around this point you sample some pictures, you'll get Romit's face like this, like that. No, right? Why not? Because around that point, 4,000 dimensional space, right? So in the neighborhood, 4,000 dimensional neighborhood, there are lots of junk. There are lots of noisy faces of Romit. There are lots of pictures which are my eyes over here and this eye over here. All of that is in that 4,000 dimensional ball around my picture. Only a few of them is my face this way, my face that way, this way, and so on. Right? So even in that 4,000 dimension, you have to go in the right direction to pick my face in different orientations. You go in the wrong direction, you get my eyes next to my lips. That's the hardness. So that's the first level of hardness. Even if you sample around this region, how do you sample the right one? And the second level of hardness, which no one's done this, solved this, is can I sample far from things that I've already seen? Good. Okay.
This question, sorry. Is there a formal or is there a way to even define what is creative versus hallucination, or is that
very open? Last year, NeurIPS paper. In fact, Jan LeCun's recent comment is this creativity is really lacking because we don't know how to mathematically define it. Even humans cannot define it. Modern art. Some people say this is junk. Some people say this is fantastic. Right? Creativity, like artists draw eyes that go out of the face. That's creativity. That's not consistent with reality. So that boundary is very hard. Okay. So bottom line, we want to fit f theta x to our data. What is data? All pictures that we can get from the internet. All real pictures we can get from the internet. We want to fit this function, and we want to make sure this function is a probability distribution, probability density function, parameterized by theta. Meaning the neural network's parameters will learn this. And our hope is this distribution should approximate the true data distribution. Who knows the true data distribution? Who knows the true data distribution? God. We want to learn this so that it approximates the true data distribution, but we do not know the true data distribution, only God knows. That's a high level goal. And the assumption is we have enough data points X, we have enough images that it represents the true data. So if we crawl the whole internet and get all the images, those images cover the whole data distribution. That's the assumption. Okay. Generative models ideally want to learn, or at least if I cannot learn, even if I can sample from p theta x, that's good. Do you see the difference? I don't need to know the function. If I can sample from that function, maybe that's fine. Okay. Generative models have this goal. Good. And there are four main pillars of generative models: variational autoencoders, generative adversarial networks, normalizing flows, and diffusion models. And let me give you a quick overview of what these four things are, and we'll dive into each of them through the rest of the day. Okay. Latent space models, autoencoders, and variational autoencoders. So this is the hypothesis with latent space models. It says, God generates these images, right? Actually, God does a very simple thing. God has a bunch of rules. And basically, it samples the rules, puts those rules together, and generates an image. So if we want to generate images, we just need to learn those rules and the distribution on those rules. Okay? If we learn those distribution on the rules, then we can sample from the rules and generate images. So for example, maybe God's rules are any picture are a combination of squares, circles, vertical lines, rectangles, horizontal lines, and triangles. So God may know that any picture I can create by picking from these shapes with some distributions and then putting them together, stitching them together in a certain way so that that image will come, right? Here is a better way to understand this. Imagine I show you all pictures of an incomplete played chess game. Okay? I take all pictures of incomplete chess games from the internet, right? And I want to basically now generate new pictures that are also incomplete played chess games, but they should be correct, right? This is a generative model, you see, right? And now one way to generate new pictures of incomplete played chess game is if the generative model learns, oh, the first pixel has to be white. If the first pixel is white, the second pixel has to be black. If the first pixel is white, second pixel is black, the third pixel has to be white. That's one way of learning. Another way of learning is, hey, forget it. Let's learn the rules underneath this chess game, underneath all these pictures. And the rules could be, oh, the bishops always go diagonal. The rooks always go horizontal and vertical, right? If you can look at these pictures and learn the rules, then if I ask you to generate a new picture, you can say, let me sample the bishop, sample the rook, sample the pawns, put them together, and the picture will get generated. Right? So these are called latent variable models, because to learn the picture, you're actually learning some latent rule underneath it and generating new pictures from that rule, as opposed to trying to understand the pattern in this picture, in these pictures. Okay. Good. So this is basically learning the rules of chess. And mathematically, that will be defined as the following. If I give you a chessboard image pictures, you have to basically come up with a conditional distribution that says, given these pictures, what rules or what rule has maximum probability? Hey, look at this distribution. Q you can think of as P, probability. Probability of a rule given the set of chessboard pictures. Does that make sense? I show you a bunch of pictures and I ask you what rule explains these pictures, right? You know, right? In chess, black bishops are always on white squares, right? So if you look at a bunch of pictures, you should be able to say, black bishops are never on black squares. That's your rule number one. And if you learn that rule, every time you generate a picture by sampling that rule, you will never generate a black bishop on a black square, right? So you learn these rules one after the other, and basically you learn this distribution. Okay. And now, of course, this is for one chessboard image. Oh wow, this is cutting it out. Sorry.
We should have changed the resolution.
Oh, can you do that? That would be great. I can keep going, but yeah.
You may able to know the rule for Bishop. You may able to know the rule for vertical and horizontal. Yes. Right. Because can be different that you may have learned that.
Right. So don't take it too literally, right? If you do not know the rules, you might say that, look, if you get incomplete pictures of the same chess game, maybe from those you can say, I never see the bishop going diagonal. And if you do not know, then you don't have anything to say about rules. So your rules may not be perfect. I'm giving a very crisp example. In reality, your rules might be, whenever I see blue on top, there's a strong chance of green at the bottom in the picture, because most of the outdoor pictures are blue sky and green grass, right? And then you can say, the rule can be, no, you can refine the rule. If the picture is bright, and if I see blue on top, there's likely some probability green at the bottom. So these are the rules. Yeah. So now if you take the expectation of this distribution over all images, all chessboard images, you see this conditional distribution, if you take expectation over X, you get actually the rules, which is probability of Z. Why is this alpha? Because you're going to learn this with a neural network. So you learn the rules of the chess game with a neural network. By the way, no one has done this. This is very hard to exactly learn the rules of the chess game. But for images, you can learn some rules that you cannot interpret, you cannot explain, but there are some rules. Hey, is that clear? What I'm saying with chess, I'm giving you this example because the rules in this case is very clear. But with a real neural network, they're going to learn some rules which is not interpretable. The neural network understands those rules. For humans, we don't know what that rule means. The neural network has learned some pattern, but that pattern is good enough to generate new pictures. Okay? Good. Oh, I cannot do that. Jaden? No? Okay. Actually, maybe it's okay. I can say it. Yeah. So now once you learn QZ, which is the distribution on rules, you sample from QZ and you create images from it. So this is what a variational autoencoder will look like. There will be an encoder which will take images and it will generate rules. Okay. There will be a decoder that will take these samples from these rules and generate an image. And we'll ask this encoder, you'll train this encoder decoder in the following way. You'll say, here is an image of a chessboard, or here are a bunch of images of a chessboard. Can you learn some rules such that when you sample from those rules, you create the same images once again? If you learn a wrong rule, you won't be able to create the same images. Do you see that? Only when you write the right rules, and maybe the right rules are not unique, there might be many possible rules. But if you learn one possible right rule, you might be able to create the images, and you train this neural network by saying, hey, your generated image and your input image should be identical, which means whatever rules you learn, when you decode from it, you get back the same answer. Does that make sense? So you train this with self-supervision. You make the neural network learn itself, whatever the data is, and that's how you learn the rules. And typically the rules are in very low dimension, much lower dimensional space. Images are in 4,000 dimensions. Rules may be 128 dimensions. And that's nice, because to create these images, you've learned a rule that is much smaller. And these are called VAEs. And we'll dive into VAEs much more closely, but for that, we will need some amount of probability, particularly maximum likelihood and expectation maximization. We will talk about that soon. Okay. Now, questions? Guys, if you can, feel free, please.
Yes. You said earlier that the phase thing, right? Like, oh, I need to figure out those specific paths which generate different specific.
Right.
So this kind of self-supervision, how does it sort of teach you that? Because you're just generating the same things that you're seeing and you're learning rules, assuming they're correct.
Right.
So how do you know this?
Right. So that's a good question, right? How do we connect that manifold notion that we had with this? If the rules are correctly learned, right, you will always generate consistent pictures, right? If the rules are wrongly learned, you'll go out of the manifold. You see that? Right. So when you train this neural network, you're essentially saying, learn a rule such that you are in the manifold And that manifold is pictures of this. In this case, the manifold is exactly my face is pictured. Right? So in this case, if you learn the rules right, you're going to generate exactly my picture. But the rule will say the face has 2 eyes, 1 nose, 1 lips, and has a facing direction. Later, what you would do for generation, oh, I don't have a slide for that. What you'll do for generation is the following. You'll remove this encoder completely. And you have only rules. And you just sample from that rule. Right? And if the rule said that, oh, the person's face is facing this direction, and that's an axis, that's a rule. If you sample from that, the person's face will be facing in different directions. Right? So you learn a distribution over here, and you sample from that distribution, and hopefully every sample from that distribution will still lie in the manifold because you've learned the correct rules.
So are you just like minimizing the loss function that you
Correct.
So like a certain data set, or you just generate random like inputs and then just keep trying, or it still needs a data set?
Yeah, you always have a data set, and you train this by saying, learn the rules such that you recreate the data set absolutely correctly. Okay, but we'll add some more terms to that loss function later. But for now, it's good to say you should learn such a set of rules that it helps you generate that data exactly. Please.
So you use the operational keyword hopeful in that you use the operational keyword hopeful.
Hopeful,
right?
yeah.
Hopefully you will learn it, right? So how do you sort of make that you're confident that learn? So I guess maybe you go through this.
Yeah. So we will dive into it in much more detail. I'm saying hopeful because when you reconstruct from those rules, you're going to have a loss function.
Yeah.
You're going to minimize that loss function, right? And you're not going to be able to minimize it perfectly. So you'll have some errors. That's why I'm not saying that it will always generate exactly that much.
It's a goal to pick the joint distribution or just marginal or
The goal is to get QZ given X. Expectation over all images. So what will happen is in the Z space, for every X, you'll have a Gaussian. Okay? Which is saying for a given picture, I have a rule that's a Gaussian QZ given X. And then I would take an expectation over that, which means it will be one Gaussian for one image, another Gaussian for another image, another Gaussian for another image. And the whole rule space will be a mixture of Gaussians. Right? And in that rule space, then you'll say, let me sample from that rule space. So I'll sample from the mixture of Gaussian, and then I'll decode and I'll get new pictures. Things will become clear. This is an overview. Okay. Then came GANs. Okay? And GANs says, hey, forget all this rule business. Okay? What are you doing at the end of the day? You have a Z. By the way, this latent space is called Z space, C. And images are called X. So GANs said, you are taking some point in Z and converting it to some point in X. Here, you're sampling from the rules and you're getting an image. And that Z space is how many dimensional? 128. X space is how many dimensional? 4,000, right? So GAN says, you guys are too intellectual. I don't care about all of that. You have a 128 dimensional space. You want to take a point from that and you want to convert it to 4,000 dimensional space. This is all you're doing, right? So why bother about all those rules? Let's do the following. We don't need those distributions on the rules. We just need to generate samples. Who cares about their probability values? So this is what it says. Look, at the end of the day, so GAN is saying, I'm going to sample from the latent space, some low dimensional space, forget latent, 128 dimension. And I'm going to sample with a Gaussian distribution. If I sample, it's all going to be random 128 dimensional vectors, right? And I somehow need to learn a network which will transform these 128 dimensional vectors into 4,000 dimensional vectors that should look like realistic pictures. That's my goal, right? But look, how do you train this? Suppose you take a neural network and you say, hey, here is a 128 dimensional vector, change it to this picture. It figures out a way to change, right? You can take another point over here, but then these 2 points have no relationship, so you cannot take another point and say, change it to a cat. That training is very hard. Okay? So GANs said, no, we are going to do something smarter. So here's the smart. GANs said, I'm going to first train a neural network that I'm going to call generator. And this generator's goal is to take this 128 dimensional Z value, I'm going to call it a Z value from now on. Take a Z value, which is going to be noise, junk, right? 128 dimensions. And I'm going to ask it to generate some random pictures. It can be realistic, it can be junk, whatever, doesn't matter. But these are fake pictures. Okay? It will generate something. My goal is to make these fake pictures go closer and closer to realistic pictures. I need to somehow train it. That's my goal. But I don't have the solution yet. I just have trained a neural network that generates junk pictures. But then what I'm going to do, by the way, these junk pictures also lie on 4,000 dimensional space, agree? Because they're also points in 4,000 dimensions. Now this is what I'm going to do. It says I'm going to take another neural network and I'm going to show this neural network 2 things, real pictures and fake pictures. And I'm going to ask this neural network, hey, between these real pictures and fake pictures, can you tell the difference? Remember, real pictures and fake pictures will all lie in 4,000 dimensional space, right? And this guy is called a discriminator, essentially a classifier. And I'll tell the classifier, hey, can you tell apart between real pictures and fake pictures? Suppose the classifier does a great job in separating them. What does that mean? If the classifier separates it perfectly, who did a bad job? The generator did a bad job, right? Generator's goal is to try to make the classifier not do a good job, right? If the discriminator cannot separate it, who did a bad job? Discriminator. Right? So you train both of them together by saying you generate some random pictures, but you have to fool the discriminator. And the discriminator has seen the real pictures. Discriminator is seeing the fake pictures. When you train it, the discriminator knows this is real, this is fake. It's training. So over time, what happens is the discriminator learns to separate them better. The generator tries to not let the discriminate separate them better. As a result, the generator's pictures get closer and closer to the real pictures. Right? Because if the generator generates real pictures, then the generator has fooled the discriminator, even though the discriminator is trying hard to not get fooled. That's serving our purpose, because our purpose at the end of the day is, I don't care what this discriminator does. My purpose at the end of the day is to generate real pictures from the generator. Right? So if you look at this from a distribution point of view, the generator generates pictures that follow some distribution, but initially that distribution is fake, bad distribution, because it generates pictures from this distribution are junk, right? My eyes over here, right? My hair over here. Right? Those are all junk. But over time, because the discriminator can easily separate between the true images and the fake distribution, it can separate. The generator is going to try to move this distribution closer and closer to the real image distribution. Did you see the animation? Okay. And once it has done that, then for any generated image, the discriminator will say, I don't know what to do. I think this is half probability that it's real, half probability that it's fake. I've served my purpose, which is I have now generated an image which is difficult to separate. And then I forget the discriminator. I only take the generator and I generate images from it. This distribution matches that distribution. So I just generate samples from this distribution, I get realistics.
Here also you still have to learn the rules to get the rules.
But you see, right, I didn't learn it explicitly, right? What the generator learned, I don't know. It's some neural network learned something. But in VAE, I forced it to come up with some latent space.
So the generator is generating initially random stuff.
Random images. So when I train, I need both discriminator and generator. But when I generate, I don't care about the discriminator anymore. I only use the generator. Sorry.
How would you compare like the autoencoder with this like adversarial model? Like which one would you use under which method?
That's difficult to say because both of them have different properties. But one big property is that this has known, okay, let me point this out. This generative model has not learned the distributions. It has only learned samples from that distribution, right? Whereas the VAE learned a distribution. That's a difference. But this guy, empirically, people have seen that it generates better, sharper images, although it needs many more images to train. We'll get into some of those details.
Would it be better if the starting point you have some data that so that it does not do random stuff, and so you have a starting point, right?
You mean over here?
Yeah.
You have a starting point in which you have some real data, you mean?
Yeah. So if you already trained with some starting points, then would it be better?
Can someone answer that? Can someone think through that? So his point is, instead of starting with random noise, right? Why don't I start with some real data and then try to get to real images? But then what am I doing? If this is real data, so this is a picture of a cat. I'll make it a picture of a cat or I'll make it a picture of a human. Right? My goal is at the end to learn a distribution in some space where I'll sample from that distribution and I'll generate new images. If you put real data over here, then you don't, first of all, you don't know how to sample the distribution because the real data distribution you don't know. Right? You want something that's very simple like a Gaussian, right? Very easy to sample. And every point in that Gaussian will give me a real image. That's the goal.
You have to build that and generator can learn to like just do nothing.
Yeah, exactly. Right. If you put real data over here, the generator will take the image and just pass it on. Right? This is my perfect. You ask me to generate a real image, I generate a real image by doing nothing. Absolutely.
So you were mentioning GANs are not learning the distribution.
Yes. GANs are implicitly learning a distribution. That's why they're called implicit models. GANs are not learning the distribution explicitly. It's learning the distribution through samples. It's like you don't read probability theory. You just do a couple of questions, or you do many questions on probability. Right? So you look at samples of that theory and you learn it.
Well, in both cases, start with the Gaussian in a lower dimensional space and then pass it to a deterministic generator. So what is different in terms of architecture?
Because here you have started with one fixed Gaussian. In VAE, your QZ, the latent space distribution is open. You learn what is the right distribution. So you have much more control on what distribution you have on the latent space. Okay. Next, third pillar is called normalizing flows. Okay, let's start with GAN. Okay, can we claim that GAN maps noise distribution to data distribution? Can we make that claim? Meaning, I sample from noise, I give it to a generator, generator generates real data. Can we say that, hey, that is essentially starting from a Gaussian distribution on noise and generating real data distribution? Can we claim that? We cannot claim that because here is one example that GAN can do, and GAN is perfect, which is all pictures that come from here, GAN maps that to a cat, real cat, or different kinds of real cat. Do you see what I'm saying? Every point that you give from here to a GAN generates a real cat. Discriminator will say, oh, I cannot figure out if it's a real cat or a fake cat. That means generator has done a great job. You agree? But every picture is mapped to a cat. Cats are not the whole data distribution, right? Cats is just one probability in that whole data distribution space. But there's no way to hold GAN responsible for that. This is what is called mode collapse. GANs can generate pictures from one realistic looking mode. Mode means high probability regions. And that's great because GAN has served its purpose, which means it has not learned the full data distribution. So we want to do better than that. We want to make sure that when GAN generates, it should generate a cat, a human, a dog, a sky, a animal, building, everything, which is hard. So then mathematicians, okay, in the math department, people know things like the following. If you give a mathematician a simple distribution, they know how to convert it to any other distribution under some rules. The functions that convert them should be invertible and so on. Forget that for right now. Mathematicians know if you give them a Gaussian distribution, they know how to apply some functions so that this Gaussian distribution becomes some other distribution that you want. Okay, now do you see the connection? What was this?
Cats.
Huh?
Cats.
No, this is Gaussian in Z. So this is my noise, right? And this is my data. So then I can say, oh, I have a very mathematical, clear way of transforming this distribution to that distribution. Okay. So that's Gaussian, that's PX. There's a way to learn one-on-one mapping. And then you can ask, hey, wait, why do I care about that? Right? One reason you care is different points over here. In GAN, all these points could get mapped to cats, right? But in this normalizing flows, if I have a mathematical way of handling this part will get mapped to cats, this part will get mapped to dogs, this part will get mapped to humans, buildings, cars, and so on. So I have full distribution that I can transform to from a known distribution. Okay? Not only that, I can also compute probabilities of an image. Right? Given an image, a cat image, I want to ask, what is the probability of this image? What does that mean? In that distribution that God knows, if you give God the cat, God will take the cat, plug it in the distribution, and we will see, oh, this is the probability. Right? So if I can do this, so I take a point, noise point over here, it goes through some transformations and it comes to a cat over here. I can look at this probability and say, oh, the cat's probability is this much. So now we have a generative model which can also give you probabilities for images in addition to generating it. That's very valuable. Why is that valuable? If I have a picture with my eyes over here, that probability should be high or low? Low. So if I somehow generate a picture like that and I compute the probability and the probability is 0.448, so this may not be that correct. Right? So I can say I only need images that have probability 0.9 and above. Those will be realistic images. Right? So those are what the flows try to do. So we can compute probabilities of this image. And what it will really end up doing is it will basically, and this is the way we'll talk about the math if we have time. You take a sample from a Gaussian distribution and you transform it with some function. And you learn this function. But you transform it with some function until you reach the image distribution. But you don't know the image distribution. So what you'll do is you'll do it the other way. You'll take images, which is basically samples of this distribution, and you'll learn invertible functions that go to the Gaussian distribution. So you're asking the neural network, take real images, modify these images, keep modifying, fk, fk minus 1, so on, fi, f1, ultimately f1. So keep modifying these images until you get to a noise. Take another image, keep modifying that image until you get to a noise. And if you train that neural network, because of the mathematical properties, it's reversible. So now you take a random noise and you apply the same function, the inverted function. You keep doing the opposite transformations, you come to an image. Hey, yeah. No, this is what you're going to design. You're going to design the neural network with K functions, and you'll give it an image, and the neural network will say, I'll do a first small transform, then another transform, then another transform, so on, until I come to a point. And if you do it over many images, you'll train the neural, you'll force the neural network such that all those images come to this space and they become a Gaussian. If the neural network is trained on this, then you sample from the Gaussian, and if you go backward, you'll get to an image. And you know the probability of the image. Why? Because you know the probability of the point in the Gaussian, and you take that probability, you pass it through all the inverted functions, you get the probability of the image. So this is very, very cool. The problem is these invertible functions are difficult to design, and we'll see later, if time permits, that you have to compute a Jacobian. Jacobian is basically a derivative of a vector valued function. It's a matrix. Computing the Jacobian takes a lot of computation overhead. So therefore, normalizing flows are still not as popular, but a lot of research is going on, because if I can crack that, I have beautiful outcomes. Okay, lastly, the jewel crown, diffusion. This is the most popular one. Okay? So we'll look at diffusion in many different ways, but here is the high level takeaway. And this is, if you want to take away one thing from this tutorial today, might be diffusion. Because the other stuff I feel you can read and get most of it by yourself. This, we struggled. We spent multiple summers. So this is the place where maybe it's good to take away as much as you can. Okay. You all agree that it's hard to learn PDX. PDX is that D is for data, which is what God knows. Right? So it's hard to learn PDX, right? But we can sample from this function. You see that if I sample from the PDX function, I generate images, right? Okay. So how do we sample from that function? Because that function can be an arbitrary function that the neural network has learned. Right? Ultimately, we will learn P theta x, which will approximate PDX. Remember, right? That's the final goal of neural networks. Right? So we want to sample from P theta x. What is theta? The neural network parameters. Right? So this P theta x is some complicated function that the neural network has learned. Okay? And we want to sample from it. Hey, it's not easy to sample from a complicated function. So here comes this French physicist, 1947, who says, I will show you how to draw samples from any arbitrary function fx. Any arbitrary function. Right? But to do so, you have to give me derivative of log fx. Okay. Do you see that? He said, I don't want to say I'm the French physicist, but Langevin is a French physicist. He says, you give me any function, I'll give you samples from that function. He said, really? You can do that? That's magic. Langevin says, no, there's a caveat. You have to give me derivative of log of x. And we'll look at this later. If you take a distribution, the peaks of the distribution, the peaks of fx, matches the peaks of log of fx. Okay? This is an interesting thought. Okay? So this is what Langevin would do once you give him log of fx. We don't know how to get log of fx right now. But say we figure out, we give it to Langevin, Langevin does this. He came up with this equation which says, you do gradient descent using this function or this expression, xt plus tau equals xt plus tau, tau is the step length of gradient descent, times grad log of fx plus some term that's a noise term. Okay. So what is this? What is this in plain English, guys? Those of you who've done gradient descent. what curve, what function are you ascending, or what contour are you ascending? Which function are you ascending on for this? Log of fx, right? Very good. If you did not have this term, where would you end up? The local max of log of fx, agree? But the local max of log of fx matches with the local max of fx. So that's good, right? But I want samples. So which means if I only go to the local max and give you that, that's not samples, right? Imagine there's a local mountain. I want samples from that mountain. Means that I want samples near that region in X, right? Around that, in all different points on that mountain. This noise term gives you that sampling ability. So this is a very simple yet very powerful equation that says if you follow this, you are basically going to get samples from that log of fx distribution. And because the peaks of log fx matches with log fx, sorry, peaks of log fx matches with fx, I have samples from fx. Beautiful actually. Okay? But the problem is to get one sample, you have to do gradient descent for 1000 steps, get one sample. Next sample, you again start from a random point, do gradient descent. Because you started from a random point, are you going to come to that same mountain? Maybe not, right? You're going to get to some other local maxima. You go there, your noise term will give some sample. So for every sample, you do 1000 iterations. Very expensive, but nonetheless solves the problem. Okay? So bottom line, okay, so yeah, this shows that log fx and fx's peaks match. Okay? Bozita.
So, I mean, yes, you go to the maximum, but if you're underlying distribution Gaussian, you don't only want some maximum.
Exactly.
Variance, you want some more.
But that's what this noise term is going to help you do. The noise term is saying the gradient is highest in this direction, but you don't go along the gradient, you add some noise to it, so you go some noise in some other direction which is away from the gradient.
You can actually
Prove that, totally, completely prove that it gives you samples from this distribution, provided you do this for many iterations. This is completely proven. Very good. So what is the bottom line Langevin is bringing us? If I can get grad x log pdx, right? This is called the score function. If I can get the score function, I'll give you samples from pdx. But you have to figure out how to get the score function. Oh, remember, right? Log, okay, let me quickly give you an intuition. Where are the peaks of fx? It's where grad fx equals 0, correct? Look at grad x log fx. What is this? This is 1 by fx. Do you agree? Now, if I ask you, where are the peaks of this? Where is it 0? You see, it's 0, whereas grad fx is 0. Sure. Okay.
Log is not increasing, so it's
Right.
not the same.
Exactly.
For sure. But why even log? Like, why not I just do it? Like, if I just want to ascend this mountain, why am I ascending log fx mountain? And not
Yeah. So look, Langevin is a mathematician, physicist. He said that if you can get this, you can climb that mountain. If you have PDX, of course you should climb that mountain. But if you don't have PDX, I'm giving you some surrogate which you can use to climb that mountain. How do you get the surrogate? I don't know. And we'll see in the next slide how we can actually get this surrogate. Right? But log fx happens to be one surrogate which will help you climb the PDX mountain. There could be others. 20 years down the line, someone might say that, oh, e to the power x by something will also help you climb that mountain. Maybe, but this is one possible climbing. So that's the bottom line. So then the question is, how do I get grad x log fx, log pdx? That's the big question, right? Langevin hasn't solved anything for us because it still needs the score function. So here is the idea. This is kind of changed the whole game. This is, let's say, all the data, and there's a distribution over here, which is p data x. Okay? So now imagine you create some new samples Y, which is the data plus some noise. So you just take the data and you noisify it. You take a cat image, you add some Gaussian, sprinkle some Gaussian noise on it. Okay. You see, this image, which is let's say a cat, if you sprinkle some Gaussian noise on it, it will go here, right? You agree? So Y, the distribution of Y is kind of a band around the true data, where the band is like taking a Gaussian filter, blurring filter and blurring all the images, assuming N is Gaussian. Is that clear? Y equals X plus N. If you look at the distribution of Y, it's basically you look at every point in X, you take a blurring filter and you just blur around that image, all those images. Difficult? Good, right? Okay. Now, if you calculate grad log Py, it turns out beautifully that it becomes expectation of Ex given Y minus Y. Okay. Expectation of Ex given Y is an MMSE estimator. If you remember your random process, but forget if you don't remember that. What is E of X given Y saying? It's saying, I give you Y, which means I give you some point in this gray region. And I ask you, hey, how did you come to that point? Right? Means which picture did you noisify and that brought you to this point in expectation? Right? So you're kind of trying to guess the picture that got you here. Right? Y is Washington, DC. X is wherever you came from, your boarding airport. I give you Y, and across all these people in the room, I say, what is expectation of X given Y? Meaning on expectation, where did you come from and arrived in DC, where Y is DC? That's what you're asking, right? So in some sense, this is some kind of estimate of what that image is, right? Which got you Y. And if from that you subtract Y, what is that? Some image X that brought you to Y, right? And Y is X plus N. And from that you're subtracting Y. This is the noise. Some statistic of the noise that you added. So it turns out score function is a denoiser. So if you can somehow learn how to, if I give you a noisy picture and you can somehow learn how to denoise it, you have score. And if you have score, you can do gradient descent on log fx. If you do gradient descent on log fx, you got samples from fx. Okay. So score function is a denoiser. So now what do? You do the following. You take your images. Hey, at the end of the day, what do you want to do? You can start from any random point and you want to do gradient descent so that you arrive at this green point. That's what you want to do at the end of the day, right? So at every point, you need some gradient. Do you agree? Tell me if it's, slow me down if it's not clear. At the end of the day, I want to do gradient descent on this space, which means I need grad log fx on this space. Grad log fx is coming from noisifying X with some Gaussian. So if I noisify these data with a large variance Gaussian, I will basically get points anywhere in that space. Okay? So I will use a big Gaussian, get score function everywhere. I'll use a smaller Gaussian, get score function in a smaller space. Smaller Gaussians get score function. And then I'll do basically gradient ascent on that space. And I'll end up at an estimate of X hat, which is a true image. I can start at a random point in image space and use score to ascend log of fx, log of p data x, which I figured out from here. And then I have real image. Okay. Now, diffusion has been looked at from many perspectives. This is just one perspective. Another perspective is, actually the people who invented diffusion is from thermodynamics. in Stanford. The way they got the intuition was the following. They deal with physics and chemistry and stochastic differential equations and these kind of things. And they saw that if I drop a ink in a glass of water, the ink dissolves and it becomes blue water. So you can think of that as some image that's getting destroyed and becoming white noise, right? So some information, right, where the ink dropped is a valuable information, that kind of dissolves and becomes blue water. And because they talk about thermodynamics and differential equations, they know what that process looks like. And they say, hey, this process is similar to images, where if I can learn how an image becomes noise, then I can go back from noise to that image. So they talk about how differential equations can take a blue soluble water and go back to the point where the ink was dropped. And this has similar intuitions. I start from noise and I go down or I climb up to the point where that image got noisified to come to this noise. I know this is vague, but I just want to give you rough keywords and intuitions as to what is going to come throughout the rest of it. And there are people who have looked at diffusion as a hierarchical VAE. They're going to look at that as well. But the big goal or the big takeaway is that, in fact, this is the quote that the person who created diffusion said. Quote says, going from images to noise is easy. Do you know the quote? Going from images to noise is easy. Going from noise to images is called generative models. So this is the big philosophy, the big takeaway point. I have a soluble water, blue water. I want to go back to the point where the ink was dropped. I have random noise. I want to go back to the point where a real image, where that random noise came from an image. You see the parallel, right? And that's the parallel we chase mathematically. And it's very, very nicely done. Mathematics is very clean, actually. And all of that is going to come through the rest. So let's zoom out. Our goal was f theta x, which should be p theta x, which should be the distribution that God knows. Generative models want to learn. Sometimes they'll learn, sometimes they'll not learn, but they should at least be able to sample from p theta x. And these are kind of the pillars of generative models. And I hope you have some idea of what each of these pillars would do. Of course, I know you didn't understand fully, but this is roughly the full landscape of generative models. I'll learn rules and I'll generate images from those rules. I'll do game theory. I'll pit a generator against a discriminator to make the noise images sharper. I will use mathematicians in mathematics department to learn transformations from images to noise. I will use thermodynamics, differential equations, hierarchical rules to basically start from some noise point and do gradient ascent until I come to the mountain peak or near the mountain peak. And at that mountain peak, there will be real images underneath. This is the whole space. And again, we will take a short break and we'll maybe continue after we're done with the questions.
Silly question.
No silly question. Huh?
How did you start?
Random.
But depending on what you were generating,
Very good. Very good. So diffusion models can generate in two ways. One is unconditional generation and one is class-guided generation or prompt-based generation. So unconditional generation means, hey, diffusion model, give me a new picture. Diffusion model generates a picture. So in that case, it starts from some random point. Now, if you say, diffusion model, give me a cat wearing a hat, what will diffusion model do? Diffusion model will use that prompt to redefine that distribution. So that will be a conditional. That will be a redefined distribution. But on that conditional, it will start from a random point and go up. But because it's a conditional distribution, all peaks of that conditional distributions are cats with hats. And then, depending on which peak it goes to, there will be a red hat, white cat, black cat, and so on. Right? So it will generate that conditional distribution and gradient descent on that. Question? Okay, if not, What's coming up next is some probability jumping jacks. But before that, we'll take a quick short break, and then we'll start with VAE. And I think VAE is hopefully going to be interesting because the visualizations and the equations are. We'll see you in maybe 5 seconds.